Hello, my name is Hongjie Yang. I'm the Director of ICT Policy and Regulation Department of Huawei Southern Africa region. Distinguished participants, ladies and gentlemen, good morning and good afternoon. Huawei would like to thank Forum Global for the opportunity to share with you the result of our study on satellite usage in the C-band. Huawei is a leader in the mobile technology and ICT technology. More than 200 carriers have used the Huawei product solution in Africa, and Huawei has served over 900 million people in more than 50 countries in Africa. We can legitimately say that we are expert in mobile technology. The 3400 to 3800 MHz band is the key for the development of 5G in Africa as well as globally. Huawei is leader in 5G network equipment for this band. However, it is also a band that is important for satellite service. The satellite C-band from 3600 to 4200 MHz has been in use for many years. There is now excessive demand from the mobile side and the satellite side. For the frequency in this band, it is important to consider carefully how the band can be shared band between these two competing services. If we here, I mean the mobile industry, the satellite industry, and the regulators and the policymakers aspire to evaluate this question properly, then it is important to have good information about these two services. We are not experts on satellite communication in Huawei. We do not manufacture satellites or ground equipment. We do not operate satellite-based networks. We know very little how the satellite business works or how big it is in Africa. This lack of knowledge is a problem for us when we look at the question of how to share between mobile and satellite. Unfortunately, there is not much information publicly available on this. Therefore, we have sought information ourselves. We have asked satellite experts to look at these questions for us. We have asked the system house who are based in Johannesburg to look at the applications that use C-band satellite connectivity, the number of satellites serving the continent, the capacity they provide, and how much of that capacity is being used, the deployment of Earth stations, how can interference from mobile service can be mitigated, and how can the satellite service be mitigated out of 3600 to 3800 MHz. System House conducted the bulk of their work during the last months of the 2020 and January this year, and the second phase of analysis about a month ago. We have found the results from System House are very interesting and sometimes surprising, and we want to share them with you. To be clear, the purpose of today is not to promote mobile service in the band, but bring to you the evidence that we have gathered about the satellite usage. The lack of information is a real concern in our view. And we hope that this study will initiate an open discussion with the satellite industry about their actual usage of the band. To facilitate this, and in addition to the presentation today, we have published a report from Systems House so that it can be scrutinized by everybody. It is available in the GSA website. I will now give the floor to Roy Brach. Roy Brach is the owner of the System House, a niche consultant based in South Africa, offering the advisory service to the telecom industry, focus on fiber, wireless, and satellite technologies, as well as data centers and supporting infrastructure. Roy has over 25 years experience in the satellite industry and has provided advisory service to numerous satellite operators, broadcasters, system integrators, and VSAT service providers. Roy is the electronic engineer, having obtained a BSA from University of Cape Town in 1991. Roy Brach will go through the study and the result. If you have questions during Roy's presentation, please use the chat and we will relay them to him. Thank you and enjoy the presentation. Roy Brach, now floor is yours.
Thanks, Mr. Hongjie. Good day to everybody. I'd like to take you through the brief summary of the study. As Mr. Hongjie indicated, the bulk of or the full report is available on the GSA website for you to review in detail. First slide, please. So as indicated by Mr. Hongji, this study was commissioned by Huawei in October 2020, and we finished it in Q1 of 2021. The main areas that we focused on were initially to review the main C-band satellite applications, and then to perform an assessment of the usage of the C-band spectrum, specifically the downlink band from 3.6 to 4.2 gigahertz. For this, we looked at two areas, or we obtained data from two areas. One was market research data from Northern Sky Research, and secondly, we did measurements on 37 satellites. Then we did an assessment of the fill factor, which I will explain during the presentation. And then we also looked at the quantum of C-band VSAT terminals in Africa used for different applications. We did a review of some interference aspects pertaining to the use of this band for both satellite and IMT services, and looked at some mitigation approaches. And then we also did an analysis of some of the migration options that could be considered in order to free up the lower portion of the C-band for IMT usage. Thank you. Next slide. So for starters, just to define what we mean by the standard C-band, this is in satellite terms from 3625 to 4200 megahertz. There are other variants of the C-band, including the extended C-band or the INSAT portion as shown in this table. But we were primarily focused on the downlink band in the standard C-band, which is 3625 to 4200 megahertz. Important to note that in the data that we got from Northern Sky Research, they look at the entire C-band, so being all of the above bands, when they look at capacity, demand, as well as number of terminals. So then in terms of the differentiation of the different types of satellites, this is really broken down into fixed satellite services, which was the traditional satellites being used for the last number of years, typically with wide beams, analog transponders, bend pipe operation. And within this category, we have two classes, those which are station kept. In other words, they're maintained within a narrow orbital position so that a VSAT terminal, a fixed VSAT terminal, can operate with them. And others that have potentially reached the end of their life and they're in inclined orbit, where one needs tracking antennas on the ground to be able to communicate with those satellites. Then the new generation of satellites called high throughput satellites. These typically have narrow spot beams, digital payloads on most of them. They have a high frequency reuse across the beams, and really, as the name indicates, an order of magnitude more throughput than fixed satellite services traditionally had. Next slide, please. So just to provide a brief introduction to how fixed satellite service traditional transponders work, in the image on the right, you will see a simple representation of this. Essentially, a VSAT will transmit to the satellite. The satellite receives the signal. It has a input filtering and low noise amplification stage. It then does a frequency translation, re-amplifies the signal, and transmits it back to the Earth. So a very simple repeater in the sky. That's how traditional satellites worked. New technology satellites like Amos 17 use digital payloads, and these are far more advanced and include digital demodulation, switching, baseband processing, remodulation of the signal, and they allow a much greater level of flexibility in terms of how capacity can be switched between beams and between different services. So one can have small and disparate segments of capacity allocated to specific beams, and based on demand, this capacity can be shifted between the different beams. Next slide, please. So if one looks at a typical satellite transponder plan, and here I've used an example from Intelsat 1002 with its coverage footprint shown on the right. So for starters, there's a number of different beams on each satellite, or on most satellites. The satellite, for example, has a global beam, which is the wide outer circle ellipse that one can see. It has hemi beams, which are shown by the red outline section, so one covering the Americas and one covering Europe, Africa. And then it also has zone beams, which are shown by the yellow shaded sections. Now, the satellites typically use dual polarization. In many cases on C-band, it's circular, but there are a number of linear satellites, linear polarized. And there's frequency reuse. So every channel can be reused on, for example, right-hand circular polarization and left-hand circular. What one can also do, if you look towards the right of the transponder plan, you'll see that a single transponder can be used on any of the beams. So, for example, transponder number 10, if it's being used on the global beam, as I indicate there, then it can't be reused on the HEMI or the zone beams because their coverage areas overlap. If you look at transponder 11, I've indicated it might be being used on the zone beam, in which case it can't be then used on other overlapping beams like the global and HEMI beam. So, pardon me. So there is some flexibility to allocate transponders to different beams. What one will also notice is there's a guard band between the different transponders, as shown by the blue arrows. And then also to point out that the cross-strapping is where one is able to, for example, have a satellite terminal in Brazil and one in Zambia and be able to interconnect the two by cross-strapping the two transponders. So the signal is uplinked from Zambia, downlinked in Brazil and vice versa. Next slide, please. Okay, so what are the reasons why people continue to use C-band, or why people use C-band on satellites? The first is, if you have a network deployed over the continent, for example, and you have existing C-band ground equipment, there's a much lower upfront cost if you just reuse the equipment. In many countries, there's logistical challenges to get new equipment into the country, installed and commissioned. And so in many cases, it's often simpler just to continue using C-band because of the equipment that's already on the ground. Another well-known reason is the high link availability. Typically, 99.9% is easily achievable on C-band. On other frequency bands, one can get high availability, but this is typically through use of adaptive modulation, where you effectively trading off throughput versus keeping the link up and operational. Same technology as used on mobile platforms and wireless terrestrial systems. And then another major advantage of C-band is that you can get really wide beams, as shown by this example in the bottom right for Intelsat 20, where, for example, the landmass beam essentially covers multiple continents, very useful for a service provider that wishes to deploy a network with sites all over those areas, or for maritime operation where you're operating, for example, between India and Africa. So it provides the ability to have a single network with VSAT sites over a very wide geographic area, which helps in efficiency and lowers cost and complexity. Next slide, please. Okay, what are the main C-band applications in Africa? So for starters, television is a big one. And we divide it into three areas: contribution, distribution, and direct-to-home. So contribution is where the broadcasters are receiving TV contribution leads at their main facilities, including these in their bouquets, and then distributing those. In the distribution side, this is often to terrestrial towers as well as to other broadcasters, where a TV broadcaster will send out their bouquets to terrestrial towers for onward transmission to the end customers via UHF or VHF. In terms of the African market for direct-to-home, there's, as far as all the data we can ascertain, there's no usage of C-band for direct-to-home. So that's where a consumer has a VSAT dish at their house for television reception on C-band. Then another main application is enterprise VSAT, where cellular forms a really big component of that on C-band. So, and here we divide into two areas. One is cellular backhaul, where the actual base station has a VSAT and the connection is directly to that base station. which we understand is around 3 to 5% of the subscriber backhaul done via satellite. And then the other is cellular trunking, which is where you backhaul the base station to a local aggregation point, might be within a specific town or city, and then from there you have a large satellite trunk to backhaul that capacity to the MSC or BSC, wherever that might be. And that's typically not reported as satellite backhaul, but rather as trunking or some application. Other enterprise VSAT users of C-band are oil and gas industry, air traffic control, and the military. And then in terms of volume of traffic, there are some other users such as international trunking, banking, mining, retail, and hospitality, but these form a very low percentage of the total capacity use. Next slide, please. So as we obtained data from Northern Sky Research, which is a well-known market research company in the satellite industry. What we present here is data for Sub-Saharan. We also obtained for Middle East and North Africa, but in the interest of time, we won't present that. So what one sees in the top right graphic is, first of all, the top brown line is the total supply in what is transponder equivalence, in 30 megahertz transponder equivalence, which is a unit of measure in the satellite industry. Then the bar graphs indicate the total demand, and the brown line indicates the revenue that the satellite industry will get from C-band services on FSS satellites over the next 10-year period. So what the key observations that one can make there is that there's a significant decline in the supply and the demand. Most of the demand is as a result of reduction in the enterprise segment, which is the yellow bar. The unit price of bandwidth will halve over that period, and revenue will fall by around 70%. Also important to note is there's no broadband or direct-to-home usage of C-band, according to Northern Sky Research, and very minimal government telephony and mobility usage. TV distribution and contribution at the bottom dark blue section, as one can see, that remains fairly constant over time and will continue to be a big user of C-band capacity. Then what's interesting to note is that in 2019 or 2020, they indicate the fill factor is around 90%. So the demand is 90% of the supply. And in 2029, that drops to around 75%. For high throughput satellites, at the bottom right plot, and here the y-axis is in gigabits. You can see a sharp increase in usage of high throughput satellites over the next 10 years, with enterprise data providing 95% of that demand. And the bulk of this is backhaul. Around 94% we calculate of that demand is coming from backhaul used in cellular and other operators. Initially, at the moment, there's a fill factor of around 10%, so there's a lot of surplus capacity, but that increases to 65% in 2029. And just to point out that the trends are similar for Middle East and North Africa, but in the interest of time, we won't present those. Next slide, please. So in terms of summarizing the total C-band satellites over Africa, we did a desktop research on this. Shows that there are 54 satellites which cover Africa or a portion thereof, and that could just be a small segment of West Africa or the Horn of Africa or something. So at least some coverage of Africa. There's 54 satellites. These utilize around 37 gigahertz for FSS satellite. There are also two high throughput satellites, those being AMOS 17 and Intelsat 35E. In our estimations, they have utilize around 6.3 gigahertz of capacity. And then towards the bottom of the table, we see that the number of satellites with C-band coverage of Johannesburg is 43. Of those with elevation angles above 15 degrees, there's 41. And in our measurements of the satellite, we measured 37 of those. So it was a significant portion of the total population. Next slide, please. Okay, so if one looks at this as indicated, the satellite beams can cover much more than just the African continent. And if you look at the examples, the pictures at the bottom of the slide, for example, you'll see that the Hemi beam can cover Africa and large parts of Europe and Russia. The image on the right shows, I think it's VSAT, that covers primarily Pakistan and just a small portion of the whole Africa. So in order to determine the total capacity available in Africa, we allocated different percentages in terms of the type of beam that the satellite used. Those are shown in the graphic there. So the net result is, if you look on the graph on the right, that in total there's 899 transponder equivalents of capacity on those satellites. Once we've done the apportionment, that reduces to 502. For inclined orbit satellites, that drops from 134 transponders to 89. And on the right, for high throughput satellites, we fully allocate those to Africa because those beams are really dedicated to Africa. Next slide, please. Okay, in terms of the measurements that were done on the satellites, we measured from 4 different teleports in Johannesburg using a variety of sizes. Just to point out that these measurements are representative of the measurement that you'd make anywhere within the satellite beam. So if a beam covers the whole of Africa and we measured it in Nigeria and South Africa, the downlink spectrum would look pretty much identical. We measured from 3600 to 4200, that being the band of interest. These measurements were done late last year. And for each measurement, we took a minimum, a maximum, and an average plot for around a minute, which gave us enough time to capture any bursting TDMA carriers, like one normally gets on the in-routes of VSAT networks. Then what we did was we set a threshold to assess whether there were carriers present on a specific resolution block, the resolution bandwidth, or not. And on the basis of that, we then applied a transponder plan. So if you look at the plot on the right, the green rectangles indicate Hemi beam transponder specific satellite. The yellow indicate global beam transponders. And we then basically did a full factor analysis of every transponder and the satellite as a whole. So in this example, on this polarization, I can't quite read it, but I think it was 88% full factor. And in the bottom portion of this graph, you can see the full factor on each transponder. So we did this for both polarizations on every satellite that was measured on all 37. To be able to get detailed insights into the full factor and utilization on each satellite. Next slide, please. So to summarize the results, we also did the full factor analysis for different subbands. So for example, in the 3600 to 3700 megahertz band, we found that the full factor was around 35%. Substantially lower than the average for the full band. And we believe this is probably because of existing issues with WiMAX interference and such like that have caused service providers to try and not use this band, the lower portion. So on average for the full band, you'll see from 3600 to 4200 megahertz, the average full factor was 57% for the 37 satellites that were measured. Next slide, please. This indicates the different satellites and the measured full factors on each. It's the average of both polarizations, sorted from lowest to highest. As indicated, the average was 57%, the lowest usage was around 18%, and the highest 86%. The full details you can find in the report that was referenced on the GSA website. Next slide, please. What we also then did was looked at this quantum of C-band terminals in Africa. Again, we sourced data from Northern Sky Research from their VSAT and Broadband Market Report, the 19th edition. What is excluded from their report are maritime terminals and also receive-only terminals. So receive-only terminals are still exceptionally important, specifically for the TV distribution signals. And we did a detailed assessment of that and estimate around 2,000 C-band terminals are in use for broadcast distribution to towers, to terrestrial towers. If one looks at the graphic on the right, some important trends are a 3.5% compound average reduction in the next 10 years in the number of terminals. And the main decrease is in the backhaul and trunking segment, which would probably indicate they would either shift those to terrestrial services or to other frequency bands, as would be the case if there was terrestrial availability. Typically, that would be for backhaul in most instances. And then also to point out that these terminal numbers, averaging around 23,000 in 2020, seem significantly higher than many in the industry would estimate. But we're going with this data from Northern Sky Research, given the volume of work that they do and the quality of it. Next slide, please. So what we then also looked at is the capacity utilized per application to give us some insights into where the dominant usage is. And if we focus on the graph on the right, the red bars indicate the percentage of the total sites, and the blue indicates percentage of the total traffic. So what is very obvious from this is that the backhaul and trunking is, whilst it's only 31% of the total sites, it contributes around 77% of the total capacity use. The next biggest user is TV distribution and contribution, with around 19% utilization. That means that the remaining roughly 9,000 terminals used in banking, retail, hospitality, and other enterprise areas uses less than 0.6% of the total capacity on C-band. So there's really two main users, with it being a much lower tertiary usage. What's also important then to realize is that if the mobile industry wishes to have access to the C-band spectrum, they would be able to contribute significantly by reducing their backhauling and trunking requirement. And given the percentage of the total capacity used by that application, it could make a significant impact on the demand for C-band. Next slide, please. Okay, we're looking now briefly at some interference mitigation and migration strategies. So what we assumed here was, if you look at the image on the right, is that for argument's sake, let's assume we allocate 3.6 to 3.8 gigahertz to 5 to IMT services. We have a 20 megahertz guard band, and then the satellite systems would be able to use from 3.8 to 4.2 gigahertz. So the 5G out-of-band interference levels, which would be present within the satellite receive band, those are specified in the 3GPP standards and various other supporting standards. When one looks at interference situation on a VSAT terminal, you have to take into account both the user equipment and the base stations. Many analyses we saw only took into account the base stations, which is probably not a fair reflection of the real interference environment. And to point out that every situation is unique in terms of the azimuth and elevation angle separation between a VSAT terminal and a 5G base station or user equipment, the satellite's noise temperature, its antenna patterns, its side lobe levels, the 5G base station and the ERP in the direction of the transmit power in the direction of the satellite terminal, what the frequency separation is between the two, what the distance is between the two, and what the propagation characteristics are. For example, is there foliage? Are there trees? Is there an actual physical shield between the two? So every scenario is unique, So it's very difficult to perform a general analysis. And then also when one looks at the tolerable interference level on a VSAT, it's a function of the whole link, but not just the receive noise, which is often used in the calculations. So that includes factors such as the satellite's cross-pole interference, adjacent satellite interference, what have you. So it requires a very detailed analysis in order to determine the impact of the interference on the satellite link. Next slide, please. So we looked at a number of options to mitigate the interference and characterize those in terms of whether they reduce the in-band 5G level, they reduce the out-of-band 5G level, or they improve the satellite's link. So the first is if you reduce the power from the base station or the IMT user equipment, that will reduce the in-band and the out-of-band levels. If you improve the transmit spectral mask on the 5G or IMT equipment, it'll improve the out-of-band levels when receives on the satellite terminals. If you add filtering on the satellite terminal, that reduces the in-band level. It stops the satellite terminal's front end from saturating, but it actually decreases the link, satellite's link performance. It actually worsens it, and we'll cover that in a following slide. If you add shielding, it can reduce the in-band and out-of-band levels. If you increase the physical separation, it also has the same impact between the physical separation between the 5G devices and the satellite terminal. Then if the VSAT moves to a different satellite where you get greater angular separation from, for example, a nearby base station, that can potentially improve the link budget if the new satellite provides a better link budget, but it will definitely reduce the in-band and out-of-band 5G levels. If you increase the satellite terminal's antenna size, that may have an impact on the out-of-band levels because of lower side lobes, perhaps, but it will definitely improve the satellite link budget. That's one way of improving the carrier level as opposed to trying to reduce the noise level. If you increase the satellite's carrier power, that will improve the satellite link budget, but this is not always a possibility. Every transponder has finite power. When you lease capacity, you get an associated amount of power with capacity. And if you use more than your power allocation, generally a satellite operator will bill the service provider for that. So it's not a straightforward approach to say, well, we can just increase the satellite power to overcome interference. And then lastly, you could entirely change satellite band. If you're running on C-band and you've got significant interference, you could migrate to a KU-band service, retrofit the VSAT terminal, and avoid the C-band entirely. Next slide, please. So what is the impact of any filtering on VSAT terminals? So the filter reduces the 5G signal below the level that saturates the VSAT, LNB, or LA, the front end of the VSAT terminal. It has no effect on the 5G out-of-band interference because this is all within the passband of the filters and where the actual VSAT system wants to receive the satellite signal. The filter introduces insertion loss, which negatively impacts on the satellite link budget. In the calculations that we've done with different examples, it shows that if you add a filter to a VSAT terminal, you would probably require 25% more bandwidth because you have to reduce the coding or the modulation in order to make the reduced performance based on the addition of the VSAT filter. The plots on the right just give you an idea of the effect of filtering. The top plot is a 7.3 meter antenna where there was, if you look under the green, that's the max hold plot. There's significant 5G interference on this satellite terminal. You'll see it also masks a satellite carrier shown in the pink circle. And if one adds filtering, like the lower plot where it's a 4.5 meter antenna with a filter, you can see that the relative level of the interference is substantially reduced, which stops saturation of the front end of the receiver and allows user to actually still receive their signal within the C-band where the satellite carriers are. So it significantly reduces the interference, it stops saturation, but it also has a negative impact on the satellite link budget. Next slide, please. Okay, so if we look at different migration options to vacate the lower portion of the C-band, there's really 4 options that we've looked at. Option 1 is where you say, well, we're going to migrate the network to the same satellite using the same beam and the same polarization. So I'm just going to move up to a different frequency transponder. In that case, such a change can be done remotely from the VSAT hub normally. Doesn't require a site visit to the VSAT terminal unless you need to add a filter, and it's fairly easy to implement. Option 2 is if you same satellite, but now you move to a wider beam. So let's say you were on a zone beam, you move to a hemi or a global beam using the same polarization. You need again to do a site visit if you fit in a filter on that site, and it can be done reasonably easily with minimal impact on the network. In the third example, this is where we're using the same satellite with the same beam, but a different polarization. In this case, you need to do a site visit to actually rotate or change out the feed polarization on every VSAT terminal that's going to be migrated. So in this case, it'll take a substantial amount of time, probably at least an hour per VSAT site. And you would need to have a dual illumination. So you need to have a network running on the one polarization and one on the existing polarization so that you can migrate sites between those as the field installers visit each site. And lastly, you could move to a completely different C-band satellite. This obviously requires you to repoint the VSAT antennas in the field and to potentially change their feed polarization and possibly also fit a filter. Again, it's a fairly lengthy process, at least 2 hours per VSAT once the field installer is there, and it will require dual illumination. So you'll need to have a network running on the new satellite and the old satellite so that you can handle migration of sites, your remote sites between the two. Next slide, please. If we looked at migration option 1, we analyzed this in a lot of detail using the measured spectrum for each satellite that we have. This didn't take into account the additional bandwidth that may be required if filtering is needed. It also didn't look at specific carrier packing and grooming considerations. And what's also important to point out is that if the 3.6 to 3.8 portion of spectrum is used in a specific area. For example, in this plot here, we show it's getting used in East Africa in the red circle. Then in the remainder of the African continent, as long as one doesn't have any VSAT sites on a network in that area where it is allocated for IMT services, you can carry on using the 3.6 to 3.8 gig spectrum on the satellite. It doesn't, the policy of whether you're using 3.6 to 3.8 for IMT or satellite doesn't have to be applied as a whole across the continent. There can be a variable application and use of the spectrum depending on the country or region. Next slide, please. So to give you an example of this migration option, this plot shows one of the satellites we measured, which has a number of 36 megahertz transponders. As you can see that there are 2 vacant transponders at the high frequency. This blue circle, blue rectangle indicates the 3.6 to 3.82 gigahertz spectrum. So if we were trying to free up that spectrum on this satellite, we'd have to move these carriers in the lower 3 transponders up to the vacant transponders. Of course, as you can see in this example, there's a shortfall, about 18 megahertz. So while some carriers could be moved, there's certainly not enough capacity on the satellite to accommodate all of those carriers. Next slide, please. So In terms, we basically ran an analysis on all of the measured data that we have. If you look at the table, it indicates that if we were to try and vacate the 3.6 to 3.72 gigahertz portion of the spectrum, we'd have a total shortfall of capacity across the satellites we measured of 316 megahertz, which is 2% of the occupied bandwidth. And in total, 9 of the satellites that we measured would actually have a shortage. The rest, we believe, would be able to accommodate the shift of carriers into higher frequency transponders. If that band was increased to 3.82 gigahertz, we'd have a total shortage of 2 gigahertz, 12% of the total occupied bandwidth. And in that case, 23 satellites would be affected. And this is only for migration option 1, where you're looking to move to the same satellite on the same beam and the same polarization. The shortage would be less if you used one of the other migration strategies, but as indicated, they are more time consuming, could be more costly, require field visits, and so on. Next slide, please. Thank you.
Thank you, Roy. I don't know if Hongji is here or has there any final comments or anything on that. If not, then we can wrap things up. So, okay. Well, look, thank you, Roy. Thank you, Hongji. So, yeah, really appreciate that. I see Hongji's back, so I'll leave you to wrap things up, Hongji.
Yeah, it's fine. I think it's a good topic we discuss, and the start in the future we discuss about the C-band, how we can, all this knowledge can be shared and the discussion. And Roy's report is valuable, and in the future we can see how that. And if you're interested in report, you can get it from the GSA website. Thank you very much.